Trigonometric substitution. Let's consider the following problem. Suppose that A is a positive entity and we would like to evaluate the primitive of square root of a squared minus x squared divided by x squared dx. Let's assume for a second that this guy is not there, and instead we have an x upstairs. So in this new situation, we could have used the U substitution, right? The substitution rule, because the derivative of the radicand is negative 2x. A is supposed to be a constant, right? Positive constant. So negative 2x would have been the derivative of the radicand, and we have an x outside. So the substitution rule could have been effective in this scenario. However, the problem as it stands is more difficult. So what I'm gonna do, I'm gonna set x to be a sine theta. Why I'm doing this? It's an observation that people have discovered. Let me illustrate it for you. So if you set x as such, then what happens to the square root of a squared minus x squared? So this becomes the square root of a squared minus, the x is a sine theta, so a squared sine theta becomes, sine squared theta becomes a x squared, right? The x squared guy. And this is equal to the square root of, let's factor out a squared inside, and we get 1 minus sine squared theta, right? Okay. And this is equal to square root of a squared. Since a is positive, square root of a squared is a, times square root of 1 minus sine squared. 1 minus sine squared. And how much is 1 minus sine squared if you appeal to the Pythagorean identity? Back to the trig course. So this is cosine squared theta. Correct? So then this is equal to square root of cosine squared theta. Okay. And what's the square root of cosine theta? Well, it depends what theta is. Correct? If cosine theta is positive, the square root of cosine squared theta becomes cosine theta. And if cosine theta is negative, then the square root of cosine squared theta becomes negative cosine theta. So we don't know what theta is at this point. So this is going to be simply the absolute value of cosine theta, right? I mean, that's the case anyway. But my point is, we don't know if it's plus or minus. We don't know if we want to drop the bars. We don't know if it's going to be plus cosine theta or negative cosine theta. It's plus cosine theta if cosine theta is positive, and negative cosine theta, right? The absolute value of cosine theta is negative cosine theta if cosine theta is negative. So dependent where theta lives is going to determine whether we're going to have a plus or minus sign for this cosine. So I'm going to keep the sign alive. We know it's going to be plus or minus if I'm going to destroy the bars, right? So I'm going to keep the sign alive. Obviously, it cannot be both. It's one thing. So it has to be either positive or negative. I'm going to keep the sign alive just for a second, and in the sequel, I'm going to be able to determine which of the sign between plus or minus. Okay, so this pink part is still alive. We have to determine which one of the two signs we have. Alright, so the point here, the square root has been destroyed, right? The square root has been destroyed. Now we have an entity which has no square root in it, correct? So using this trig identity, we were able to actually kind of destroy the bar, destroy the square root. Okay, and then so if x is a sine theta, what is dx? What is dx? The differential of x. Dx is a times the derivative of sine, which is cosine theta, d theta, right? Correct? So this implies this and it's also implied by this. Okay. All right, so as such, what can we say about this integral then? How about we give it a name? So let's give this integral the name I. So thus I becomes was the integral square root of a squared minus x squared. Well, square root of a squared minus x squared, we said it's either plus or minus a cosine theta. So I'm gonna keep that sign again alive. Remember, it has to be one or the other. And upstairs becomes a cosine theta divided by the square of x, and the square of x is the square of a sine theta, so it's gonna be a squared sine squared theta. And dx is a cosine theta d theta. Okay, now let's do some simplifications. Let's keep carrying that plus or minus, and we're gonna have primitive of a times a divided by a squared, that's 1, cosine squared theta upstairs, right? Cosine squared theta upstairs divided by sine squared theta d theta. Okay, all right, let's keep carrying this plus or minus. Remember, it's gonna be at the end of the day one of them, but this is why I put it in a different color, just to keep paying attention to this. And then this is cosine theta divided by sine theta is cotangent, so that's gonna be the square of cotangents of theta. So cotangent squared theta d theta, right? And cotangent squared is cosecant squared minus 1, right? So this guy is cosecant squared theta minus 1. So this is going to be equal to plus or minus the primitive of that entity, cosecant squared theta minus 1 d theta, right? Okay. And if you split the integral, what do you get? All right, so we get plus or minus. Actually, how about we do it immediately? So we're gonna split the integral and then integrate, right? So primitive of cosecant squared, what's the primitive of cosecant squared? It's minus cotangent theta, right? Because cotangent theta, if you differentiate it with respect to theta, I get negative cosecant squared. So that's gonna be then negative cotangent of theta, right? Minus primitive of 1 d theta is theta, right? So you get this, plus a constant of integration, Okay? All right. So let me actually take this equality just down here. So now this answer is in terms of theta, and this is not what the question was about, right? The question was given in terms of x. So we have to represent theta back in terms of x, right? Okay, let me start by this guy. Over here. I want to write theta in terms of x, correct? What's x in terms of theta? It's a sine theta, right? So I want to solve for theta, which forces me to talk about the inverse of sine, right? I wanna talk, because if you want to solve for theta here, you would get sine theta is x divided by a is positive, so different than 0. I can divide by a. So sine theta is going to be x over a. But then to find theta, I want to talk about the inverse of sine, which is the arc sine function, correct? And as such, theta has to be in an interval where sine is 1 to 1. And by this I mean the arc sine is going to exist, right? The inverse function is going to exist. And such an interval is minus pi over 2, right? Remember from the trig class, sine inverse, oops, let me change this. So sine inverse is a function that goes from minus 1, 1 all the way to minus pi over 2, right? So you restrict sine, this is the restricted version of sine, from minus pi over 2 so that the inverse exists, correct? So this is taking you back a little bit to the trig course. So theta has to be in the interval minus pi over 2, the closed set, minus pi over 2, so that arcsine is invertible, or so that sine is invertible, so arcsine exists, and as such I can find theta in terms of x, correct? So this is I mean, we're used to introduce the new variable in terms of the old variable, right? In the substitution rule, we used to write the new variable in terms of the old one. Here we're writing the old one, the one that the integral was given in, the x, in terms of the new one, correct? Such integration is called inverse, such a game is called inverse substitution. And we need to talk about inverses in such a case, okay? All right, so over here, I'm gonna go back now. I'm gonna go back to this, and I'm gonna adjust my understanding of theta, because I wanna talk about arcsine to get back to x. So I'm gonna then say with theta being in minus pi over 2. Why am I doing this way? Because again, I want to talk about theta in terms of x. So as such, you're gonna talk about arcsine. So you want sine to be invertible, and arcsine is defined if you restrict sine on this interval, right? Okay. All right. And as such, with this choice of theta, what can you then determine about cosine? Well, theta is in either the fourth quadrant or the first quadrant, right? So as such, cosine is certainly positive. So the absolute value of cosine of theta becomes simply cosine of theta. So it's technically the positive sign, not the negative sign, correct? So I'm gonna erase the minus. I'm gonna keep it in the notes just for you to remember. So it's positive based on where theta lives, right? Theta lives either in the fourth or the first quadrant. So as such, cosine, the absolute value of cosine becomes simply cosine because cosine is positive there. Okay? All right, so I'm gonna erase all these, keep it like this. All the minus, it wasn't the minus at the end of the day, it was the plus. Okay? All right, so then I can find theta in terms of x. So x is a sine theta, and this means since theta is in this interval, arcsine then exists, and then we're talking about sine theta being x over a, which means theta is arcsine or sine inverse of x over a. And again, the reason is since sine is invertible, right? So since sine is invertible, which means theta is an interval which allows sine to be 1 to 1. Okay, so we're restricting the attention of we're restricting the domain of sine so that it becomes invertible, and the universal restriction for sine so that we can talk about arcsine is actually minus pi over 2, correct? Okay, so this is then the relationship. This is actually theta in terms of x. It's right there, correct? That's theta in terms of x. So I'm done with this part. This is good now. I know what it is. Now cotangent of theta. I need to write cotangent of theta in terms of x. Well, I have Sine theta written in terms of x, it's right there. It's this one here, right? I have a relationship between sine theta and x. So to find cotangent of theta in terms of x, I can use trig identities to transition from cosine all the way, to transition from sine all the way to cotangent, right? So one such relation can be, you can find cosine of theta in terms of sine by using the Pythagorean identity, and once you find cosine you can get cotangent, because cotangent is cosine over sine. If sine is in terms of x and cosine is in terms of x, then you can get cotangent in terms of x, correct? So this would be one way to do it. Another way is something that you've seen in your trig class too. Let me draw it here. So it's a diagram. It's a right angle triangle where theta is the angle facing or where theta is one of the angles that are involved in the triangle, right? So this is a right angle triangle, and let's say theta is here, okay? And if sine theta is x over a, one such triangle is a triangle whose hypotenuse is a and whose opposite side to the angle theta is x, correct? This is a right angle triangle that allows me to get sine theta, where theta is this guy, to be x over a, correct? So x becomes this guy, and a becomes the hypotenuse, because sine, remember, sine is the definition of sine based on right angle triangle is opposite, the length of the opposite side divided by the length of the hypotenuse, right? So we get this, correct? Okay. In this discussion, theta is, I'm supposing that theta is positive. In this diagram, theta is supposed to be positive, which may not be the case, right? Because theta can be negative as well. Look, theta lives here. It can be positive, it can be negative. Let me just think about theta being positive for a second, and I'll discuss theta being negative just shortly, okay? So if theta is positive, I can have this game, and sine theta, since sine theta is x over a, then I can consider the triangle whose sides are x and a, and I can find the length of that blue side, right? I can find the length of this blue side by using the Pythagorean theorem, okay? And what is it? So this side becomes the square root of the hypotenuse squared minus the length of the other leg squared, right? Because the sum of the square of the legs, right, should be the square of the hypotenuse. Okay? So one more time. Pythagorean theorem says the sum of the squares of the length of the legs in a right angle triangle is equal to the square of the length of the hypotenuse. Okay? So if you do this game, you're gonna get this length is equal square root of a squared minus x squared. Okay? Alright. Let me erase this part. Alright, so once I have this situation, now what's cotangent of theta? Cotangent is, what's the definition of cotangent based on right angle triangles? Cotangent of theta is simply the adjacent angle over the opposite, right? The length of the adjacent divided by the length of the opposite side. So this is then equal to, so now we know it's a plus sign, right? So plus minus cotangent of theta, as we said, it's the adjacent, so which is square root of a squared minus x squared divided by the length of the opposite side, which is x, correct? Minus theta, and how much was theta? It's arc sine or sine inverse x over a plus the c, that constant. Okay, all right. Remember, we left something behind, which was what happens if theta is negative. If theta is negative, negative theta is gonna be positive, right? Negative theta is gonna be positive. Also, if theta is negative, what can you say about x? If theta is negative, sine of theta is gonna be also negative, right? And my point is, if theta is negative still, but bigger than or equal to minus pi over 2, correct? So if theta is here but negative, then sine of theta is definitely a negative entity, and hence, since a is positive, right, x becomes a product of positive entity and negative entity, which means it's negative. So x becomes a negative entity, right? And negative theta is positive. So since x is negative, negative x is also positive, right? Because if x is negative, you multiply it by -1, you get minus x, and becomes a positive entity. So therefore, you can play this game, but instead of having theta, you can play it for negative theta, right? You can play it for negative theta. And instead of playing it for x, you can play it for negative x, correct? And what do you get here? You get, instead of x, you get negative x, right? So negative x squared, but what's negative x squared? Isn't it the same as x squared, right? And as such, what do you get for cotangent of negative theta? Cotangent of negative theta becomes equal to the adjacent, which is square root of a squared minus x squared divided by the opposite, which is negative x, right? So you get cotangent of minus theta is equal to that, but you want cotangent of theta. And what's cotangent of theta in terms of cotangent of negative theta? Cotangent is an odd function, so it's negative cotangent of theta, right? Correct? So at the end of the day, you get that this guy is equal to this guy. What does it mean for cotangent then? If you want to solve for cotangent, you multiply by -1. You get a plus here, and this turns a plus, which means you get that cotangent of theta is equal to that. Make sense? So what I'm saying is, even if theta is negative and lives here, that result that we obtained is gonna remain the same. All right? Okay, so as such, I'm not gonna change anything. So as such, this diagram can also hold, I mean, it holds when theta is positive, but it also allows you to deduce the same entity. Cotangent of theta is equal to that, even when theta is negative, based on the discussion that we just made. Okay? All right. So let's recap, and let's try to understand what happened in the process here. So we had a situation which looked difficult. With an appropriate choice of substitution, I was able to kind of destroy the square root, right? And then the process was smooth, but I also required that the trig function is invertible, right? So I want to restrict the trig function, which was sine here, on an interval so that its inverse exists, right? So this was the process here. Let me try to transplant this trick that we just talked about and try to extend its range of application as much as we can. Technically, what I'm saying is, what if here, instead of a squared minus x squared, what if I have a situation that looks like a squared plus x squared, right? So what could have been, or what would be a good substitution here? So you have a constant plus something squared, and you would like to find a perfect square that's representing a squared plus x squared. So do you remember any any identity that's 1 plus, right? Now I'm gonna have plus something squared equals a perfect squared. I hope you remember 1 plus tan squared, and that equals secant squared theta, right? So to force this, I need x to be now, instead of a sine, I would like it to be a tangent theta, right? To get to this point, correct? And as such, things are gonna unfold as we did in the purple case. Okay, so when we have a plus, now we can make this substitution to get to eliminate the square root, and the situation or the integral becomes simpler, right? So what other, obviously I still need to restrict the tangent function, right, to an interval where it's gonna be invertible, and tangent inverse, it's universally defined on -1, 1 with values and minus pi over 2 open, right? Meaning if you restrict tangent to minus pi over 2, you can tangent inverse then exists, correct? And this is the universal restriction for tangent, to talk about its inverse. Alright, so what can be another situation? What if now, so how many cases I have? I can have plus here, minus here. I can have plus here, the one that we just talked about. I can have minus here, right? Minus here, but this situation cannot happen because as such square root of a negative number, I mean this becomes square root of a negative number, so this cannot happen. I can have minus and a plus, right? Minus and a plus, meaning that's gonna turn into a -1 plus something squared. Do you know any identity that's -1 plus something squared is a perfect squared? It's the same one that I just talked about. You can replace sine by sec, right? So secant squared -1, we know that this is tangent squared. This is the same one that I just talked about earlier. It's the same identity, but I'm solving for tangent now, right? So if I have minus next to that constant and a plus, I could have used the substitution a secant then, right? A secant theta, and still I need to restrict theta to a certain interval so that secant inverse exists. And as you know, you can restrict it. There are many ways to restrict secant, right? Remember, secant is 1 over cosine, so that its inverse exists. But the book follows the restriction for secant to be between 0 pi over 2 and pi over 2 and pi over 2 and pi. Okay, so with this choice, then I can get to this point, and then I can actually erase the umbrella and the square root here, right? They can undo each other, correct? And the situation remains very similar to the one we just had in purple. So there are 4 cases, but one of the cases doesn't work because you're gonna have minus here and minus here, so this becomes square root of a negative entity, and this cannot, this is nonsense, right? Square root of a negative number is not a real number. So you're remained with 3 cases. 3 cases, so you have minus, plus, plus plus, and plus minus, correct? And these cases are actually summarized in the next table. They are right there. So if you have an expression that looks like this, a trig substitution, a useful trig substitution would be u equals a sine theta. So you change that u to be a sine theta, and theta is between minus pi over 2 and pi over 2. So we're imposing all these conditions so that the respective trig function has an inverse, and the structure of this is gonna yield at the end this identity. So we're gonna use this identity as we saw in the first example, if you have this structure, constant plus variable squared, so use a tangent theta, because the structure here is gonna yield 1 plus something squared, and 1 plus something squared, you can take this thing to be tangent to get a perfect squared. And finally, this structure square root of variable squared minus a constant. If you choose u to be a secant, then once you factor a squared out, you're gonna get the structure secant squared theta minus 1, which is a perfect square. Okay, so these are the three situations where you can use such trig substitution. Okay, let's now consider the following example. Let's suppose we need to find the area enclosed by the ellipse, whose equation is x squared over a squared plus y squared over b squared equals 1, where a and b are positive entities. Let's give it ourselves a graph to be able to refer to that area just pictorially. So let's say this is the x and y axes, and this is the upper half of the ellipse, and this is the lower half, say, right? It's not this is not an ellipse, but just it gives you a feeling of how the ellipse is. It's a distorted circle, right? Circle is a particular case of an ellipse. This point here is the point a comma 0, where a is this guy, and this point here is the point 0 comma b, where the b here is this guy, right? And what they need is they need the entire area enclosed by the ellipse. And it's not hard to see because the ellipse is symmetric with respect to both axes. It's not hard to see that the total area is actually 4 times this guy, right? 4 times this guy. How about we call this guy regular A? The area, the green area is regular A, and the entire area is how about we call it calligraphic A. Okay, so we have the following. We have that calligraphic A is equal to 4 times that regular A. Okay, and what's that regular A? What's that area? The green area. It's the integral, right? It's the integral. Let's integrate it with respect to x, so dx. So it's the area, it's the integral of that function, which we need to find, right? Between 0 and x is going between 0 and a, right? 0 and little a, this guy, correct? So the question is, what's that function that you see here? What's that function that you see here? So let's go to the equation of the ellipse and try to understand what's that function that we see in blue. How about calling this part, this whole thing, the blue part of the ellipse? Okay, so what I'm gonna do is I'm gonna take this a little down, and I'm gonna try to discover what function that blue curve is and put it here, right? Alright, so let's find that. From this equation, I can say that y squared over b squared is equal to 1 minus x squared over a squared. Correct? And this is the same as saying if you do the same denominator, a squared minus x squared divided by a squared. Okay? And that's the same thing as saying then that y squared is equal, if I multiply both sides by b squared, I'm focusing here and here, right? These are the same. So if you multiply both sides of the equation by b squared, what do we get? We get that y squared is equal to b squared over the a squared times a squared minus x squared, right? So that's the same thing as saying then that y is equal, here x is between minus a and a, right? So this guy here this guy here is non-negative, and as such this whole thing becomes non-negative. We can then talk about the square root. So y then is equal to plus or minus the square root of this entity, which means b over a, because both a and b are positive. So b over a times the square root of a squared minus x squared, right? So we got plus and minus, and the blue one is the plus actually, right? So the upper half of the ellipse is actually the positive side, and the lower half is the negative side. In this context, we are interested in the positive side. So this curve has the following equation. So y equals b over a times the square root of a squared minus x squared. Correct? This is the blue curvature. Okay, so that's the function that's gonna sit right there. That's the function that's gonna sit right here. So b over a, right? Let me zoom out. So b over a square root of a squared minus x squared. B over a square root of a squared minus x squared. That's the green area. 4 times this becomes the total area, right? Okay. Alright, so it comes down to actually integrating this function, b over a square root, which is the same thing as 4b over a, because b over a is a multiplicative constant, so you can push it outside, primitive or integral, definite integral in this case, 0 to a square root of a squared minus x squared dx. Correct? Alright. So this is a situation where we have a square root of a squared minus variable squared, and according to what we discussed above, this is of this structure, right? This is of this structure, and then I'm gonna use this substitution because this is reminiscent, this structure is reminiscent to this, right? I'm gonna find it in the process. Okay, so I'm gonna set u to equal not u, x to equal a sine theta. Let's do that. So here I'm gonna use x to equal a sine theta, while keeping in mind that theta is an element of minus pi over 2 pi over 2, so that sine inverse exists, right? So that I can find x in terms of theta, so that I can find the old variable in terms of the new one. Okay. Alright, and as such, this becomes 4b over a. Definite integral. What are the bounds now with the new variable? If x is 0, this means that sine theta is 0, because the product between a and sine theta is 0, and a is a positive entity. We talked about it above. So, if x is 0, this means sine theta is 0. And what's the theta in this interval that makes sine theta 0? It's the 0, right? It's the 0. Correct? One more time. Theta lives here, and sine theta is gonna match 0. So what's the angle that lives between minus pi over 2 and pi over 2 whose sine is 0? There must be one and only one, and that guy is 0, right? Okay. Alright. And then when x is at the upper bound a, so when x now is at a, then sine theta becomes a over a, which means sine theta is equal to 1, right? Correct? One more time. If x is at a, the upper bound, I'm trying to find this one here, because now I'm going to have d theta. I'm changing the variable, right? So if x is at the upper bound a, so x is a, then a sine theta is a, so sine theta must be 1. And what's the angle that lives between minus pi over 2 and pi over 2, including the endpoints, so that its sine is 1? There must be one and only one guy. And that guy is clearly pi over 2, right? So let me erase this part. So this is pi over 2 here. Correct? Alright, so this is square root of a squared minus the square of x, so the square of a sine theta, right? Dx, if x is a sine theta, dx is going to be a cosine theta, correct? D theta. Make sense? Okay. Alright, and then let's factor out a squared. So let's factor out a squared, and we get from here that this is equal to a squared times 1 minus sine squared theta. That's this guy. That's this guy, right? And then 1 minus sine squared theta is equal to cosine squared theta. So this is equal to a squared times cosine squared theta, right? Okay. And then what do we get? We get that this is equal to 4b over a, the definite integral. Theta varies from 0 to pi over 2, right? And this is square root of a squared, which is a. So which is a, let's push the a outside. And square root of cosine squared theta, that's the absolute value of cosine theta, times cosine theta, d theta, correct? But theta lives in between minus pi over 2 and pi over 2. As a matter of fact, theta lives between 0 and pi over 2 in this case. As such, what do you know about cosine? Cosine is positive, right? And I mean, non-negative. When theta is at the upper bound, it becomes 0. But anyway, so cosine is non-negative, and as such, the absolute value is not doing anything, right? So the absolute value of cosine theta, given that theta is in here, absolute value of cosine theta is actually cosine theta itself. So we can drop the bars, and then we get here the a and the a cancel each other, so we get 4b times the integral from 0 to pi over 2 cosine squared theta d theta. And how do we integrate this thing? How do we integrate cosine squared? I think I missed an a somewhere. Yeah, right. So this square root of a squared is a, and I forgot to bring this a. So I'm gonna have a squared here. So this is an a here, right? Okay, so back to this. So how do I integrate this guy? So I have cosine squared. So I'm gonna appeal to the earlier section, the previous section. I'm gonna use the half angle identity for cosine squared to actually linearize the power and be able to integrate. Correct? So I'm gonna use it. I'm gonna use the formula, which is let me write it here. So this guy is equal to half times 1 plus cosine 2 theta, right? Okay. So the half can be brought outside, and the 4 becomes a 2, right? Times the integral from 0 to pi over 2, 1 plus cosine of 2 theta d theta. Okay, and this is equal to 2ba or 2ab times let's integrate. So primitive of 1 is theta, and primitive of cosine 2 theta, if you use substitution rule here, you're gonna get half sine 2 theta, and the bounds are 0 pi over 2, right? Okay. Alright, so realize here, because this is a definite integral, we didn't have to convert back to we don't have to convert back to the initial, right, the original variable, which was x. Okay, just because it's a definite one, so I can evaluate it now. And this is gonna be equal to twice ba or ab times, let's evaluate this at the upper bound, pi over 2. So I'm gonna get pi over 2 plus half sine of twice theta, and theta is pi over 2, twice pi over 2 is pi, right? Minus the evaluation of this at the lower bound, so theta is 0, so 0 plus half sine of twice 0 is 0, right? Okay. So sine 0 is 0. 0 plus 0 is 0, so this whole thing here is 0. Okay. How about sine pi? Sine pi is 0. So half of 0 remains 0. Right? So this whole thing is pi over 2 then. So this whole thing is pi over 2. So 2ab times pi over 2. Now what is that? This is pi ab if you simplify by 2, right? So it's pi times a times b. So this is the answer. This is the area of the total area enclosed by the ellipse just discussed above, right? The total area happened to be 4, not 4, pi AB, right? Pi AB. Okay, and realize that since a circle is a particular case of an ellipse, when A and B are both equal to the radius r, right? In that case, since A is gonna be r and B is gonna be r, so this becomes pi r squared, right? And pi r squared is the area of a circle. Okay. All right. So let's now move on to the next exercise. Let's evaluate the primitive of 1 over x squared times square root of x squared plus 4 dx. So here we have the structure variable squared plus a positive entity, right? So let's go back to that table and determine which structure we have. So in this case we have this structure over here, right? So a squared plus variable squared. So the u is the x and the a squared is the 4, right? We can think about a, since a is positive, we can think about a as being 2 then. So the substitution is going to be x equals 2 tangent theta, where theta is here, right? That's what's going to happen. Okay. Let's go back. So we're going to set x to equal 2 tangent theta, where theta is between minus pi over 2 and pi over 2. So that tan inverse exists, right? Okay. Alright, so as such, the integral, so this integral then is equal to primitive of 1 divided by x squared, so 4 tan squared theta, right? Square root, let's extend this a little more, so square root of x squared, which is 4 tan squared theta, plus 4, and dx, if x is 2 tangent theta, dx is gonna be 2 secant squared theta d theta, right? 2 secant squared theta d theta, right? The derivative of tangent is secant squared. Okay, and this is equal to 2 over 4 is 1/2, right? Primitive of secant squared is upstairs, so secant squared is upstairs, tangent squared theta, square root of 4 times tangent squared theta plus 1, right? If we factor out a 4 here, d theta. Okay, and what's tangent squared plus 1? That's the objective here, right? Then we wanted to set the stage for this. Tangent squared theta plus 1 is secant squared, right? So this is secant squared theta. Okay, and since theta is here, what do you know about secant? Since theta is here, this entails that secant is positive or negative. Secant of theta is 1 over cosine, right? And what do you know about cosine here? It's positive, right? So certainly this is going to be positive. It's 1 over a positive entity. Correct? I'm going to need this just shortly here. This is equal to 1/2. Actually, let's combine it with the 2 that's going to come out of this integral, right? Square root of 4 is a 2. So 1/2 times 1/2 is 1/4 times the integral secant squared theta divided by tangent squared theta times the square root of secant squared. Technically it should be the absolute value of secant squared theta, but we just discussed that secant theta is positive, so the absolute value of a positive entity is itself, right? The bars are technically not doing anything, they're just decoration in this case. Okay, all right, this should be secant, right? Secant. Okay, all right, so secant again, because I'm taking the square root, right? Square root of secant squared is absolute value of secant, so you get secant here, and you drop the bars again because secant is positive. Okay, and that's equal to 1/4 times the integral secant squared divided by secant squared is secant upstairs, secant theta over tangent squared theta d theta, right? Okay, and what is that? What's that thing? So this whole thing here, let's try to simplify as much as we can. This thing is equal to secant is 1 over cosine, and tangent squared, so tangent is sine over cosine, so 1 over tangent squared is going to be cosine squared over sine squared, right? One more time, tangent squared is sine squared over cosine squared. Since I'm dividing by tangent squared, is the same thing as multiplying by the reciprocal of tangent squared, so cosine squared over sine squared. And this is equal, if you simplify the cosine, you're gonna get, let's simplify that, right? So we're gonna get cosine theta divided by sine squared theta. Okay, so then the integral is 1/4 integral of cosine theta divided by sine squared theta d theta. Okay, and how do we integrate this thing? We can use substitution rule here, right? We can set u to be sine theta, and as such we can get the du to be cosine theta d theta. Correct? Let's do it. So let's introduce. So let's introduce the letter, I don't know, w to be, or the variable w to be sine theta. This means dw is equal to cosine theta d theta, right? That's my substitution. And that blue integral becomes 1/4 primitive of cosine theta d theta is dw divided by w squared, right? W squared. And what's that? can take the w squared upstairs, it becomes w to power -2. You integrate the usual stuff, so you get minus 1 over w plus a constant, right, of integration, correct? And taking back what w is simply sine theta, so 1 over w is going to become cosecant theta, right, plus a constant of integration. We're not done because we have to convert back to the initial variable, the original one, and that original one was x, right? That one was x. So don't forget the relationship between x and tangent. X is twice tangent theta. So I'm gonna play the diagram game, the game that I just the triangle, what is it? Right angle triangle that I had before in the previous example, or 2 examples earlier. So here I'm gonna have the angle, the 90 degree. That's gonna be my theta, let's say. Okay, let's do it this way. And what do I know? I know that x is equal to twice tangent theta. That's what I know, right? This is the relationship between x and theta. This means that tangent theta is x over 2. Correct? So what are the sizes that allow me to get that tangent is x over 2? So tangent is opposite over adjacent, right? Opposite over adjacent. So if you take the opposite to be x and the adjacent to be 2, then that does it, right? Correct? So this is such a triangle that allows me to get tangent theta is actually x over 2. And as such, what's that hypotenuse by the Pythagorean identity? The square of this is equal to the sum of the square of those two, right? Which means this guy is going to be the square root of the sum of their squares. So x squared plus 4. X squared plus 2 squared, which is 4, right? So this is how much this length is. Okay? And now cosecant of theta, which is, cosecant is 1 over sine, right? It's 1 over sine. So which means that cosecant is hypotenuse divided by the opposite, right? So cosecant then is equal to hypotenuse, which is square root of x squared plus 4 divided by the opposite, which is x, plus a constant of integration. Right? So, sorry, arbitrarily chosen. Okay, so that's gonna be the primitive of that integral that we had over here. Okay, all right. Moving on to the next one. Primitive of x divided by square root of x squared plus 4 dx. Well, sure, we can still use the trig substitution that we learned in this section. Okay, which one would that be? It's the same one as we had just in the previous part, which was x equals 2 tangent theta. But actually here the direct substitution makes the approach simpler, because if you take x squared plus 4 as your substitution, then the derivative of this has to do with x, right? And we got the x upstairs. So a direct substitution would make it simpler. So let's do that. So let u be x squared plus 4. This forces du to be twice x dx. which means half du is x dx, right? Correct. So this would be the package to actually do the u substitution. Let's do that. This is then equal to the primitive of x dx, and x dx is half du, right? Half du divided by the square root of u, right? So u to power half then. The square root of u is u to power half. Okay, and this is equal to, if you integrate this, take the u to power half upstairs and then add 1 and so on. And what do we get? We get that this is, so the u half becomes u negative half, and then you add 1, you get u to power half after you integrate, divided by half, right? Plus c, where c is an arbitrary constant. And the half divided by half is 1, so you get u to power half, which is the square root of u, right? Plus c, and clearly here the u is that guy, so we get square root of x squared plus 4 plus that constant c. Correct? Alright. So what this problem is trying to illustrate is the fact that even when trig substitutions, the ones that we just learned in this section, even when they can be employed, they may not give the easiest approach. Okay? For example, in this case, the direct substitution would have been an easier approach. Okay? So I encourage you actually to do to evaluate the same integral using trig substitution, the one I just discussed before I started this method. All right? Okay, so let's move on to the next exercise. In this example, we need to evaluate the integral of 1 over square root of x squared minus a squared, a being positive, dx. So this is of the form square root of variable squared minus a positive entity. So if we go back to the table that we talked about earlier, this one, so this is of the form square root of u squared minus a squared, and as such we can choose the trig substitution to be the variable equals a times secant theta, where theta is either in the first or second quadrant, right? For secant to be invertible, right? Okay, and in the process we're gonna be able to use this identity. Okay, all right, so let's go back to our exercise. So we have, as we said, we're gonna set x to be a secant theta, where theta is, so where theta is in 0 pi over 2 open, because secant is not defined at pi over 2, union pi over 2 all the way to pi. Okay. All right, and as such, dx becomes, what's dx? A times the derivative of secant, which is sec theta tan theta, d theta, correct? And how about the square root of x squared minus a squared? So the square root of x squared minus a squared is or becomes, so x is a secant theta, so x squared is going to be a squared secant squared theta, right? A squared secant squared theta minus a squared. Let's factor out a squared. We get minus 1, right? Okay, so this is equal to square root of a squared. What's square root of a squared? A being positive, square root of a squared is simply a, times secant squared minus 1, that's tangent squared theta, same angle, and then we get the square root of tangent squared. And what's square root of tangent squared theta? It's the absolute value of tangent theta, right? So, and don't forget where theta lives. Theta either lives in the first quadrant, and as such tangent is sine divided by cosine, so tangent there is positive, and also theta lives in the second quadrant, right? And as such tangent theta becomes negative tangent theta. What I'm saying is the absolute value of tangent theta becomes minus tangent theta, right? So tangent theta being negative here. So theta, when theta is here, tangent theta is positive, and as such the absolute value of tangent theta is tangent theta. And if theta lives here, then the absolute value of tangent theta is negative tangent theta. Correct? So this is why in many books you see that arctan, to define arctan, you actually restrict theta to be either in the first or third quadrant. So as such, tangent becomes positive, right? Anyway, so in our book, tangent was restricted on this interval so that arctan exists. All right, so we cannot drop the bars without considering two cases. So case one. When theta is in 0 pi over 2, tangent theta in absolute value becomes tangent theta, because tangent theta there is positive, right? Because tangent theta there is positive, being in the first quadrant, and hence the square root of x squared minus a squared is equal to a times tangent theta, correct? Because the absolute value of tangent theta is tangent in this case. And what can we say then about the integral? What can we say about the integral? So the integral dx, so the integral of dx over square root of a squared minus a square root of x squared minus a squared becomes equal to the primitive dx is a secant, so a secant theta tangent theta, right? That's the dx guy, d theta, divided by square root of x squared minus a squared. In this case, that's equal to a tangent theta, correct? And this becomes, if you simplify the a's and the tangent, this becomes the primitive of secant theta d theta, right? So, and what's the primitive of secant theta? This is something we found in an earlier section. This is ln of the absolute value of secant theta plus tangent theta, right? Plus a constant of integration, let's call it k. But keep in mind here, in this case, in case 1, theta is here, right? Between 0 pi over 2, which means tangent is positive, right? Tangent is positive in the first quadrant, and secant, which is 1 over cosine, is also positive. So technically, those bars can be rounded. They can be just parentheses, right? Because again, this entity is positive in when theta is in the first quadrant, and this entity is positive in the first quadrant. So if you add two entities, each of which is positive, certainly you get a positive entity. So this result is positive. The absolute values are not doing anything technically in this context. Correct? Okay. Don't forget, we still have to consider case 2. We're gonna consider case 2. I'm gonna complete the case 1, and I'm gonna get you started in case 2, and I want you to finish it on your own. So let's complete case 1. So as such, this is then this guy, and this is equal to ln. I want to go back now to the initial. the original variable, which was x, right? Which was x. I know that x is a secant theta. So I'm gonna try to find tangent, right? So I know that secant theta is x over a. I know this. So secant theta is x over a, right? And the only remaining piece is the tangent theta. So I'm gonna use the diagram again. Right, so we're gonna use the diagram. So the right angle triangle. If this is theta, I know that secant theta is x over a. This is what I know, right? Secant theta is x over a, which means secant is the reciprocal of cosine, right? So secant is hypotenuse divided by adjacent, correct? And this forces the side that's opposite to theta to be how much by the Pythagorean identity? It would be square root of x squared minus a squared, right? Because the sum of the squares of these legs is going to be equal to the square of this hypotenuse, the length of the hypotenuse. So then what is tangent theta? Tangent theta becomes this guy divided by a, correct? So tangent theta becomes this guy divided by a. So we get square root of x squared minus a squared divided by a plus that constant of integration. Okay? And this is equal to, if you combine the two, this becomes ln of x plus the square root of x squared minus a squared over a, right? Over a plus k. And ln of a quotient is the difference of the ln's, so it's going to be ln of x plus square root of x squared minus a squared minus ln of a, right, plus k. So what have I used here? I used that ln of a quotient, right? Log of a quotient is the difference of the logs. That's what I used. Correct? So we get this. And this is equal to, what I'm going to do now, I mean, keep in mind that this is a full answer all the way to here, okay? I'm just giving you a better representation of the final answer. So since k is an arbitrary number, k minus ln of a is also arbitrary, right? So I can rename k minus ln of a to be a new constant, call it c, correct? And since k was arbitrary, c becomes arbitrary too, right? So we get ln of x plus the square root of x squared minus a squared plus that c, right? Okay, so this is the result in case 1 where theta was considered to be here. Now if you move to case 2, which means that theta is gonna be now in pi over 2 all the way to pi in the second quadrant, right? Because theta is either in the first quadrant, theta is either here or here, right? This case was dealt with in case 1. This case is case 2 now, correct? So case 2, that's this part, and this forces the absolute value of tangent theta to be, so if theta is in the second quadrant, sine is positive and cosine is negative, which means tangent is negative, so the absolute value of tangent becomes negative tangent theta, right? Okay, so what can you say then about that square root of x squared minus a squared? What can you say about this then? Well, what used to be that? Square root of x squared minus a squared, it used to be a times the absolute value of tangent, and in case 2, the absolute value of tangent is negative tangent. So this becomes a times negative tangent theta, right? That is to say minus a tangent theta. Correct? And what can you say about the integral then? About the integral itself? It's going to be very similar to this, but instead of having a times tangent theta downstairs, I'm going to have a minus here, right? So the only thing that's going to differ from this case is a minus sign. Correct? So I'm going to let you finish this on your own. So then finish this. So finish this. Okay. So I'm gonna put dot 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 here and ask you to please finish it. But we understand what's going on, right? Because that's the same treatment. This is it's very much the same, but instead of having plus here, plus here, right? Now we're gonna have a minus. That's the only difference. And then just pay attention to how this thing is gonna propagate and what's gonna happen afterwards. So it's just a matter of a sign, changing a sign, but technically the substance is there. Okay? Alright, so this, with the assumption that you finish this completes this little exercise here. Okay? Now let's move on to the next one, which is part 4 of this example. We're gonna integrate, it's a definite integral, from 0 to 3 square root of 3 over 2, the quotient x cubed divided by 4x squared plus 9 to power 3 halves dx. Okay, so what's the format of this guy? Remember, power 3 halves is the same as the square root of this guy power 3, right? Correct, which is also the same as, this is the same notation for both. That's the same as the square root of the bullet and the whole thing to power 3, right? So this is what this power 3 halves is, right? It's just to recall it. So bottom line is we still have this umbrella, and the trig substitution that we've been learning in this section remains applicable, right? Okay. All right. So how can we handle this? This is of the form variable squared, right? I can think about the base being 2x here, plus a positive entity, right? So you can think about this as definite integral from 0 to square root of 3 over 2 x cubed divided by the 4x squared may be thought of as 2x squared plus the 9, which is 3 squared to power 3 halves dx. Correct? And this is of the form variable squared plus positive entity. If you go back to the table, this is of this form, right? This form here, which means that this would be a plausible substitution. So u is equal to a times tangent theta, and theta is an entity between negative pi over 2 and pi over 2, right? So that's the substitution I'm gonna have. My u in my current context is the 2x, right? And the a is the 3. So I'm gonna have the 2x to equal 3 tangent theta. All right. So let's go back to our page. So we're gonna have u. Let's write it in different color. So how about this? U to be, sorry, not u. The u is 2x. So 2x is equal to 3 tangent theta, right? That is to say, x is 3 halves tangent theta, right? And this forces dx to be, dx is gonna be 3 over 2 derivative of tangent, which is secant squared theta, d theta, and the square root of 4x squared plus 9 to power 3, right? So let's just deal with the square root by itself. 4x squared plus 9 would be square root of 4x squared. Well, that's 2x squared, so that's gonna be 9 tangent squared plus 9, right? Plus 9. So one more time. 4x squared, this guy is the square of my 2x, and 2x is 3 tangent. Then the square of that guy is going to be the square of that guy. So 9 tangent squared plus the 9, right? Plus the 9. And this is square root of 9, which is 3 times square root of tangent squared theta plus 1. Correct? And what's tangent squared theta plus 1? That's secant squared, correct? So we get 3 times square root of secant squared theta, and this is equal to 3 times the absolute value of secant theta. Where is theta again? What is theta for this substitution here? Theta is between minus pi over 2 and pi over 2. And as such, secant is positive, right? Because secant is 1 over cosine. So that guy is positive, and as such, you don't need the bars, right? Since secant is positive, being 1 over cosine of theta, and theta is, in this context, theta is between minus pi over 2 and pi over 2. This is the domain, the restricted domain for tangent, so that we can talk about its inverse, right? Okay. So that guy then is 3 times secant theta. Let's put everything back. Hence the integral. How about I for that integral? So the integral I becomes, it's a definite one, so I still have to find the bounds. Let's find the integrand. X cube is gonna be 9 times 3, so 27 divided by 8, right? 27 divided by 8 tangent cube theta. One more time. What happened here? This guy here, x cube, becomes 27 over 8 tangent cube. Why? Because x is 3 over 2 tangent theta. So multiply this 3 times by itself, you gotta get 27 over 8 times tangent cube divided by this guy, so the square root cube, right? The square root cube. So it's gonna be this guy cube, so it's this guy cube. So divided by this guy cube means 27 secant cube theta, right? And dx is all this guy. So 3/2 secant squared theta d theta. Okay, I still have the bound, don't forget about that. So when x is at the lower bound, which is 0, when x is 0, tangent of theta is also 0, right? So if this is 0, 3 times tangent theta is 0, so tangent theta must be 0. And what's the tangent, what's the angle over here? What's the angle between minus pi over 2 and pi over 2 so that its tangent is 0? That's the angle 0, right? That's the angle 0. There must be one and only one, because over here tangent is 1 to 1, correct? So meaning if you find an angle that does it, that's the only one. So 0 does it. And when x is at the upper bound, what's the upper bound? 3 square root of 3 divided by 2. So if x is 3 square root of 3 divided by 2, how about tangent? What do we get? We simplify the 2's, right? We simplify the 2's, we simplify the 3's. That's the same thing as asking tangent theta to be square root of 3. So what's gonna sit here is the theta in between minus pi over 2 such that st for such that tangent theta is equal to square root of 3, right? Correct? That's the guy who's going to sit here. I repeat, when x is at the upper bound 3 square root of 3 divided by 2, I replace the x by 3 square root of 3 divided by 2, and I want to find the appropriate theta. So 3 over 2's tangent theta is 3 square root of 3 divided by 2. Let's solve for tangent theta. You simplify the 2's, you simplify the 3's, you get tangent theta is equal to square root of 3. So I would like the theta that lives here, right, that lives here, such that its tangent is square root of 3. Correct? And who's that guy? There is one and only one angle here, right, that verifies this property. Who's that guy? If you revisit the concepts from a trig course, that guy is pi over 3, right? So that guy is pi over 3. Okay. Now we need to simplify this expression. And what do we obtain? So let me switch back to that color, blue. So this is equal to the integral from 0 to pi over 3. And let's make some room for the numerical part. So the 27 and the 27 cancel each other, right? And we obtain 3 over 8 times 2, and 3 over 8 times 2 is 3 over 16. That's the numerical part, 3 over 16. And what's left inside? So I'm gonna have secant squared is gonna be simplified with 2 of these copies. So I'm gonna be left with 1 of them, and I'm gonna get tangent cubed theta divided by secant theta, right? D theta. Okay? Tangent cubed theta divided by secant. Don't forget what tangent means. Tangent means a sine over cosine. So that's 3 over 16. The definite integral from 0 to pi over 3. This is sine theta cubed divided by cosine cube, right? This is this part. This is this part. Let's keep it the same color. This guy is this guy. Correct? And this entity, secant, 1 over secant, well, secant is a 1 over cosine. So 1 over secant is cosine. So is cosine of theta d theta, right? So again, let's keep it the same color. This piece is this guy. Correct? Actually, to be more precise, 1 over this piece switches to this, right? So it's technically 1 over secant switches to cosine. Okay? Okay, so now we simplify. Now we simplify by cosine, 3 over 16, integral 0 to pi over 3, sine cube upstairs, d theta divided by cosine squared, right? Cosine squared theta. All right? And now what I'm going to do, I'm going to reserve one of the sine theta that I have upstairs by itself, and I'm going to write the rest, which means sine squared, in terms of cosine squared using the Pythagorean identity. Okay? So what I'm going to do is I'm going to reserve one of the sines. So 3 over 16, 0 to pi over 3. So I'm going to have sine squared theta divided by cosine squared theta times sine theta d theta, right? So what did I do? I rewrote this guy as this times this, right? And what I'm gonna do now is this guy sine squared is 1 minus cosine squared by the Pythagorean identity. So 3 over 16, 0 to pi over 3. Sine squared theta is 1 minus cosine squared theta, right? So let's keep highlighting it. That guy is okay, it's the wrong highlight. Okay, let me erase these parts. Okay, so this guy is technically this guy, right? Okay, and this is divided by cosine squared theta sine theta d theta. Okay, so this is the integral I have, and now I'm gonna use U substitution. I'm gonna take cosine theta to be z, let's say. So this is equal to, if you take cosine theta to be defined as a new variable, how about z? This means that dz is derivative of cosine is negative sine theta d theta, right? So we get this, and then the integral becomes 3 over 16 remains the same. The integral, now I'm gonna switch the bounds for z, right? Now I'm integrating with respect to z. This is 1 minus cosine squared becomes 1 minus z squared, 1 minus z squared divided by that z squared, and sine theta d theta, sine theta d theta is minus dz, right? Minus dz, correct? So this is how is it's going so far. Now the bounds, when theta is at its lower bound, which is 0, when theta is at 0, z becomes cosine of 0, which is 1, right? So one more time, when theta is at its lower bound, which is 0, then cosine of 0, which is z, becomes 1, right? Z becomes 1. And when theta is at its upper bound, pi over 3, z becomes cosine of pi over 3, and cosine of pi over 3 is 1/2, right? So it's 1/2, right? So one more time, when theta is pi over 3, cosine of pi over 3 is 60 degrees, cosine of pi over 3, which is z, is 1/2. So we get this. So now we're integrating this guy, and how do we integrate that? That's minus 3 over 16, the definite integral from 1 to half. This is 1 over z to power negative 2, right? So which is z to power negative 2. 1 over z squared, 1 over z squared, which is z to power negative 2, minus z squared over z squared, that's a 1, right? dz. Alright, this is minus 3 over 16. Let's integrate. What's z to power negative 2? The primitive of z to power negative 2. Primitive of z to power negative 2 is z to power negative 1 divided by negative 1. So it's going to be minus 1 over z, right? If you differentiate this, you get z to power negative 2. Agree with me? So that's this. Minus 1 dz is z. Primitive of 1 dz is z. And this is between 1 and a half. Okay? Okay, and then this is equal to minus 3 over 16. At the upper bound, we're gonna get minus 1 divided by half. What's minus 1 divided by half? That's minus 2. Minus 2 minus the z, which is half. That's the upper bound. And minus the evaluation of this guy at the lower bound. So it's gonna be minus 1 over 1, so minus 1 minus that one, right? Okay. All right, and then minus 3 over 16 times how much is this? That's negative 2, correct? So this becomes minus the minus 2, it becomes plus 2, and plus 2 times negative, plus 2 minus 2, they cancel each other. I repeat, minus 1, that result is minus 2. With this minus, that becomes minus the minus 2, which is plus 2. With that minus 2, that's 0. They cancel each other. So I'm only left with minus half inside. So the result is 3 over 16 times 2, which is 32. Okay? So this is the value of this definite integral that we have in part 4, this one. Okay. All right, moving on to the last part of this example, which you see on the screen. So we're gonna integrate x divided by square root of 3 minus 2x minus x squared. And the way we're gonna handle this integral is I'm gonna transform this integrand into an expression where trig substitution may be employed. And the way we're gonna do it is we're gonna complete the square downstairs. So we're gonna have a positive entity plus or minus plus or minus a positive entity plus or minus that variable squared, right? That's the perfect square I'm talking about. So I'm gonna complete the square and I'm gonna pick up the price, right? I'm gonna pick up a constant so that that expression downstairs remains the same, but I set the stage for a trig substitution to kick in. Okay, so that's the strategy, that's the plan. And how do we complete the square for this guy? So this is equal to minus, let's push a minus outside, x squared plus 2x minus 3, correct? Okay, and this is equal to what? Well, if you focus here, x squared plus 2x, this gives you a feeling that I'm talking about x plus 1 squared, right? Because what's x plus 1 squared? This is x squared plus 2x, that's the one I have, plus 1, right? Plus 1. So this value is x squared plus 2x plus 1, and what do I obtain then? This becomes minus, if I want to rewrite instead of this x plus 1 squared, correct? This means I'm bringing in a new one. So I have to lose that one that I just brought to this expression, this part. So I gotta lose it, and I want to combine it with the 3, with the minus 3. So minus 3 minus the 1 is minus 4. So this is technically 4 minus x plus 1 squared, correct? Bottom line here, I'm just completing the square. So you do the way you want. That's what we're gonna get. Okay. All right, just a second here. All right, this is it. So we get this, right? And now that's equal, the integral is equal to the indefinite integral x divided by square root of 4 minus x plus 1 squared dx. Now what's the format here? Positive entity minus variable squared, right? Let's go back to that table. So positive entity minus that variable squared. So the variable is gonna be a sine theta, right? So the variable is gonna be a sine theta, where theta is between minus pi over 2 and pi over 2. So let's keep this in mind. Let's go back to that page. So we have the trig substitution in this context would be the variable, which is x plus 1, right? So the variable, which is x plus 1, is equal to a, and here a is gonna be 2 because 4 is 2 squared. So a times sine of theta, correct? This means dx, right? dx is gonna be 2 times cosine theta d theta, right? Okay, so that's then it's gonna be needed here, and the result here is the integral. Let's focus downstairs for a second. Square root of 4 minus x plus 1 squared. How much is x plus 1? It's 2 sine theta. So square the x plus 1, you're squaring 2 sine theta, so you get 4 sine squared theta. Correct? Dx, how much is dx? 2 cosine theta d theta. So 2, let's put it outside, cosine theta d theta, right? I still have the x. I still have the x. How much is x in terms of theta? It's 2 sine theta minus 1, right? Again, I'm talking about this guy here. Solve for x for me to represent this piece in terms of theta. Well, if x plus 1 is 2 sine theta, then x is going to be 2 sine theta minus 1. Right? So we get this. Okay? Alright, and what's next? So this is equal to 2 times, what's downstairs? Can we do this quickly here for the guy downstairs? What's this guy? This guy here is equal to, if you factor out 4, you get square root of 4 times 1 minus sine squared theta. And this is equal to square root of 4, which is 2 times square root of 1 minus sine squared theta. And 1 minus sine squared is, by the Pythagorean identity, this is cosine squared. So we get square root of cosine squared, which is the absolute value of cosine theta. But keep in mind, in the expression, when we involve this relationship between x and theta, in the table, don't forget, theta has to live between minus pi over 2 and pi over 2, right? Theta has to live, it's right there. Theta has to live between minus pi over 2 and pi over 2. Okay? So let's write it actually in this note. So theta here lives between minus pi over 2 and pi over 2. And what do you know then about cosine theta between minus pi over 2 and pi over 2? So either the first or the fourth quadrant. As such, cosine is positive, right? So the absolute value is not needed. Okay. All right, and then now we can have a better or a simplified version of this purple integral. This is then equal to the 2 from upstairs, and this 2 I can cancel them, right? Let me just keep it just for the first writing. So 2 sine theta minus 1 divided by 2 cosine theta, that's the guy downstairs, cosine theta d theta, right? Alright, now let's simplify. The cosine and the cosine cancel each other. The 2 and the 2 cancel each other. And I'm only left with the integral of 2 sine theta minus 1, right, d theta. Okay, and this is an easy integral to evaluate. What's the integral of 2 sine theta? That's negative 2 cosine theta minus 1 primitive of 1 d theta, that's theta, plus an arbitrary constant. Correct? Okay, and don't forget, now we have to go back and rewrite and everything in terms of x. So we're gonna appeal to the triangle, the typical diagram that we used to have. Okay, so I'm gonna have a right angle here, correct? And what do I know? I know that sine theta is x plus 1 over 2. So I know that sine theta is equal to x plus 1 over 2. Yes? So it's this. And if that's theta and sine is opposite over hypotenuse, so the x plus 1 can be taken the length of the opposite angle, the opposite side, divided by 2. So 2 can be taken to be the hypotenuse, right? And with this, what's left for this side by the Pythagorean theorem? This would be the square root of 2 squared, which is 4, right? Minus the square of x plus 1. Correct? This would be the length of this green leg. All right. Then this is equal to the integral. The result is equal to minus 2 times cosine theta. Cosine theta is adjacent, so it's the green piece divided by hypotenuse. So square root of 4 minus the x plus 1 squared divided by 2. Divide by 2, and what's that? This is this guy, right? This is this guy. So these are the same. Minus theta minus the theta. If sine theta is x plus 1 over 2 and theta is between minus pi over 2 and pi over 2, which means arc sine is defined there, theta is going to be arc sine of this, right? So sine inverse of x plus 1. So sine inverse of that guy, x plus 1 over 2. Correct? And so again, who's this guy? It's simply coming from this piece and plus the c. Correct? And plus the c. Let me keep this in purple. Plus the c, where c is clearly an arbitrary constant. Okay. So this would be the primitive of that integral given in part 5. Okay. So what was the trick here? The trick was to complete the square and set the stage for a trig substitution to be employed, and then everything follows as usual. Okay. Alright, actually I can simplify here by 2, clearly, right? I can simplify by 2. Let's actually do it, why not? So let's keep this over here. And we obtain, once we simplify by 2, we obtain that this is equal to negative square root of 4 minus x plus 1 squared minus arc sine of x plus 1 over 2 plus the c, where c is as such, right? Okay. Alright, so this completes this section.